And then Austin, you have sharing screen abilities, correct? Over there on your end?
Let's see. Yep.
Perfect.
Sorry, I didn't catch what you said about the live stream. Am I supposed to be able to join that as well, or?
No, it's just another way for people to watch who didn't get the Zoom link.
Yep.
So we also record this live on YouTube, and that way, and I'll just monitor it for if people have questions.
Oh, nice. Thank you. Oh, wait, I'm sharing my screen. Oh my God, spoilers. Okay. How do I know who's here? Is it just the three of us?
I'll be monitoring the YouTube live stream as people join there.
Nice. We got some people there. Is Gary there? I'm not starting until Gary gets here.
I told Gary. Gary said he was going to be showing up. So, but I also like to give people about 5 minutes as people come and join in.
Amazing. Okay, let me find a couple more cool photos here as we wait.
Perfect. For those joining on YouTube live stream right now, we are going to be starting in a few minutes. We're just going to give some time for more people to come and join us. But thank you for your patience and thank you for showing up. It's going to be an exciting talk.
Oh yeah, it's going to be exciting and well rehearsed. There are many never before seen figures in here.
Oh, this is exciting.
Although they're not physics figures. So, oh, here I got the. Here I'm able to pull up the live stream as well. I can see what's going on.
I'm personally very excited about the trebuchet later.
Yes, I've been meaning to do the math for the trebuchet for honestly 4 years, and this was the final, the catalyst that I needed to do it.
Yeah.
So that works well. Oh, whoops. Yeah, I'm showing you guys this Lagrangian. I'm not sharing the correct screen.
Yeah, so motivation there for people joining in on the YouTube live stream side right now. You got to stay to the end to hear about the trebuchet.
Yeah, we're gonna get there quick. So what's the deal? 30 minutes? How long should I?
You've got 30, 40 minutes, and then we got some time for questions right after.
Okay, nice.
We're gonna give it 1 more minute. I like to do 35 on the dot. 35 minutes in is always a good timing there. And you'll be happy to know I just got information that Gary is hopping on now.
Nice. Oh, nice. Okay. Yeah, I guess I'm ready, and I'll take it away.
Sure, I can give it a few more seconds there if we want. I can do a quick introduction.
Yeah, no rush here.
Okay, second like 35. Okay. I'm gonna get things going. All right. Well, thank you everyone for your patience and joining us for this month's HQP seminar. Today, we are joined by Austin de Croix. Did I pronounce that right?
It's de Saint Croix if we're gonna be French. But
I'm from West Coast. That's my bad there. We're not the greatest with our French pronunciation, unfortunately.
You can say
anyway,
de Saint Croix. It's a complicated one anyway.
Thank you. Anyways, Austin is going to be telling us about sensitive camera sensors, fluorinated methane, and medieval siege weapons. I think specifically in that order, correct, Austin?
Yes, in the order you said, not in the order I wrote it here, but having sensitive camera sensors as the first sentence didn't seem fitting. And these systems actually do all have something in common, which I only realized after putting this together. So this is a bit of a view of some of my thesis work and some non-thesis work that me and my dad did, which we'll get into at the end. So I was like, where do I start with this talk? So I took the abstract that I submitted to Ryan and I highlighted the main things. Photon detection measuring light is a thing we do. Especially we do it in dark matter and neutrino scintillation based experiments, which Canada is, I don't want to say leading the way in, but is heavily invested in. The new technology for this is these silicon photomultipliers, which I'll explain. We need to know how efficient they are. If 100 photons hit your sensors, do we measure 10? Do we measure 0? Do we measure 52? Then I'll talk a bit about, so we build a model to describe this. I won't go over it in detail because I've discussed it 1,000 times. I will talk about 2 interesting details that I discovered while building the model, which are kind of more physics interesting. I'll talk very briefly about using this light detection efficiency model to measure some properties of carbon tetrafluoride, CF4, fluorinated methane, as it is in the SPC experiment. And then I'll move on to the siege weaponry, which, not unlike an avalanche photon detector, is held at a high energy state. So dark matter and sevens, I have to include this in here out of respect for the field, but I don't want to talk about this. We think dark matter is out there. We're trying to measure its size and weight. And there's also these things called neutrinos that can undergo sevens. We're trying to study neutrinos. They can undergo a lot of other things too. So these are 2 detectors that I've worked on in Canada that use silicon photomultipliers. This first one on the left is Lolex. It exists at McGill. It's a very small cube. It has these sensors in here that measure light. It looks like this. At Queen's, we have SBC, the scintillating bubble chamber, that the cartoon of it's like this, the inner workings like this. Outside those glass jars, we put these silicon sensors. So, we're using these devices day in, day out. So backtracking, I've been hanging out with a lot of cinematographers lately and a lot of new people in general, and they've been asking me, can you tell me what your research is? What do you study? I say, well, light comes in these pieces or particles that we call photons. Maybe it's a wave, maybe it's a particle, who knows? And I say, do you know how a camera works? Well, actually, a lot of people don't know how a camera works, but I say, the photon comes in, the piece of light comes in, it hits the light sensor. And in most cases, if it gets absorbed, 1 photon gives you 1 electron. That's not a lot of electricity. It's very hard to measure. That's why you need so much light if you're going to take a good video of something. This is my friend testing out his new camera. It's clearly daytime out, and we also have a light. So we need a lot of photons to generate a lot of electrons. For particle physicists, there's a lot less light in a lot of these experiments. 1 photon, 2 photons, 1,000 photons. It's not 10 to the 10 or 10 to the 20 photons. With these devices, 1 photon comes in, hits something, a bunch of electricity gets generated, you get an avalanche, you get 1,000,000 electrons, which is really good. They're very sensitive. That's why I said sensitive camera sensors. And then people ask why though? Well, you can do physics, study the universe, do medical imaging, etc. That's a different topic for a different day. But these are two big experiments. The one on the left obviously won Canada the Nobel Prize. This other experiment on the right is a planned experiment, Pioneer. And the particle comes in, makes a flash of light. You measure the light and you do some very interesting physics, at least in the case of the experiment on the left. They did some very interesting physics and everyone else hopes to. So we use photodetectors. What really is a SIPM? This will probably be the most technical parts of the talk. Sometimes they're called SPADs, silicon photo avalanche diode. So they look like this, but if you zoom in, by almost 1,000,000 times, you see there are all these small pixels where each of these little squares is sensitive to 1 photon. So a photon comes in, that's this cross section on the right. This is basically a reverse or a backwards LED, a PN junction. The photon hits, knocks off 1 electron and 1 hole, which then, because of the high electric field, hit another one and hit another one until you get about 1,000,000. And you get a nice visible pulse that looks something like this. The reason this is really nice, not only do you have this high gain, but if 2 photons hit 2 pixels, you get twice as much electricity that flows. And if you look at how big the pulses are, you get a figure like this figure on the left, where you see 1, 2, 3, 4 photons that have hit. So you can count individual photons. You have good photon resolution, which is amazing. I'm not going to talk about this. Talking about them as electrical circuits is complicated, and they're sometimes not fully understood, but I don't have time for that. So I made this map of, there's a flash of light, you measure the light, you get some physics. But how much light do you measure? That's the photo detection efficiency. And we need to know it to do some physics. Why not just measure it? Measuring it is very hard. This is a plot from a paper where 3 different groups tried to measure the PDE. People have different results. It's challenging to do. On the flip, or not on the flip side, in conjunction with that, a lot of experiments that might cost millions of dollars of taxpayers' money will be doing stuff like this in their simulation. Optical detector efficiency call. So light's hitting it, you want to know how efficient is it? What's the chance we detect this light? It's coming in at a certain angle, could be a different wavelength. Your experiment can be at different temperatures, applied voltages, and even different mediums, gas, vacuum, liquid. And a lot of times, people will just return a number. But the efficiency definitely depends on some of these things. And we want to add more detail to our understanding and precision in these simulations. So that's the goal. There's other reasons we care. Sometimes when a photon gets absorbed and all this electricity moves around, other photons can get emitted as external crosstalk. That's a bad thing. It's excess noise in these big experiments. We need to understand the efficiency at all wavelengths to understand crosstalk. So I think I've motivated it. We've built this PDE model. This is a extremely grainy photo of the title in the revised version that I'm submitting hopefully soon. So I'm not going to go crazy on this. But how do you build a model? We're going to do this twice. First, you simplify the system. So, this is a very complicated 3D structure. We collapse it into 2D, and we just say we have a top surface, which is this quartz. We have this sandwich, very simple sandwich, the P junction and the N junction. A photon comes in through the quartz on top. It gets absorbed in the silicon. And then we have 2 probabilities. Does an electron in the P region, and it gets pulled down, make an avalanche? Does a hole that, if the photon gets absorbed deep down, a hole moving up, initiate an avalanche? So now we only have 6 parameters, 1, 2, 3, 4, 5, 6. And then we have our experimental variables, theta, wavelength, temperature, voltage, and the medium we're in. Really, day to day or experiment to experiment, these are the 2 that you will vary if you're measuring PDE. And these are what you can't control in the experiment, but what you simulate when the photons are bouncing around. Anyway, so we do some math, and you have this very simple function. It's great. The PDE is the fill factor, how much of the surface of the silicon is sensitive. The transmission, does the light make it in? Light has to make it into your camera. It has to make it into your SIPM. If you put a filter on the front of your camera, you're going to get less light in. The photons have to get absorbed. These are these W functions. And then the probabilities are, do they get absorbed and make this electricity flow and give us this nice, beautiful pulse? So really, when you do some math, it looks more like this. And I think I have almost every equation in here. And this all gets coupled into this one long equation with all these variables and parameters. And if you want to know more about this, read the paper. There's a nice, sexy statistical mechanics included in there, which I love to see. The next step, you have to look at the literature and say, what known things can we put into our model to try and predict this well? And we don't want to be fitting a billion things and have all these fudge factors. We're not doing phenomenology. We're trying to be as analytic as possible. So there's a lot of different data out there for the refractive index of silicon and quartz. I collected it all, combed through it all, combined it all to cover the UV all the way to long wavelengths. And then we build and test a model. And I did this before Claude. I would like to include. So you have the transmission, this pink line is the ray optics. People always ask, why are there oscillations here? That's very weird that the transmission changes this quickly with wavelength. And it's because of the complexity in the denominator here in this transmission function. And if you remember from second year optics course, you know, light is a wave and it can constructively or destructively interfere with itself. These oscillations are interesting. There's some nuance for them. You can check out the paper. There's the absorption. So where does a photon get absorbed? As you change the relative size of the sandwich, the PN junction, you can absorb more or less UV and IR light. So, you know, if you make your junction really big, of course, you get more absorption at long wavelengths, which is shown as these dotted lines at the back here. You do more of this, you can combine that all together and build some nice PDE curves, which I won't show here. Then you have to get your friend to measure the PDE for you, which is not easy. This is a setup we have at TRIUMF. This is excellent postdoc Harry Lewis, who took all this data with this setup after we worked on the setup together. So you have all the data, which I'm not showing yet. You have to fit it, and you have a lot of variables, right? We have 6 parameters and all these variables, but you can break it into smaller steps to make the process more robust and isolate some of these parameters. This is a table that kind of summarizes that I can't get into. The main takeaway is you understand the optics first. So the top, how the light gets in, and you separate that from what's happening inside the device. So we took this data for the FBK VUV HD3, although we're not supposed to call it the HD3. And, you know, after a lot of steps and thinking, you have this oscillating data and you can fit it and you get some parameters that describe your junction. And then you can understand how your SIPM will behave in other situations. This top plot is the relative efficiency versus angle. So as you tilt the device, the light gets more or less efficiently absorbed. And as you change the wavelength, the light more or less goes into the device. Okay, we also did this for the Hamamatsu VUV4, which I already showed a picture of earlier. You'll see it doesn't have these oscillatory patterns. The oxide thickness on top is a factor of 100 times thinner than the FBK, but they still get similar performance. So this is the data in the top right. This is a very busy slide. Really, the money plot of the paper is this plot on the left and this plot down here. This is taking the model, which is in purple, and then we extrapolate it to new parameter spaces. So these thick lines are in liquid argon or xenon, which are these detecting materials of choice. They have high refractive indices. You can extrapolate to the UV, and we can describe the PDE versus angle. And it agrees with existing data that's out there. So this is really the statement that, hey, our model works, and we can, without measuring it, we can estimate what the PD is going to be in these new phase spaces. So that's awesome. It works, and it was super easy to do. That's why I started it 2 years ago. There was a lot of nuances, and I'll discuss 2 of the interesting ones. The first one is having non-monochromatic light. So let me skip back. This is the setup that we measured the efficiency in. Up top in my science communication style, you'll see I put lamp and color chooser. So we have a deuterium lamp. This is not a laser. So it's producing light at many wavelengths. We can't select just one single wavelength. We have a spread of wavelengths that comes into the device. This is it's a very basic monochromator in there. You know, light gets shined through, it goes through the diffractions, only certain angles get picked out. So anything that falls within that angle of however thick this is, we get those different colors of light. On the right, we have some more of this angular oscillation data. And as we change the width of this slit here, the peaks get sharper or narrower because we're letting more or less light in. Very easy. We just say it has some width, but that's not the case. What we imagined is that these would just get damped. The peaks wouldn't move. It would just be like the sine wave has less amplitude, because you just expect these things to kind of be symmetric. But that's not the case. You can't just kind of naively treat this, however, and that's because, well, first I plotted it, and then I realized why that was the case. So up top, we have this smoothing weight, which is how many wavelengths get included in. And you can see that the peaks that are produced from that move. So even though we're shining the same central wavelength, the peaks do not stay at the same spots. They shift left and right. And that's because this equation, which we're averaging over when we include a bunch of wavelengths, is asymmetric in wavelength because the optical path difference is. So you actually have to understand your monochromator way better than we thought to do these ellipsometry measurements with high precision and repeatability. On top of that, the lamp isn't emitting a flat spectrum of light. So you have some Gaussian, which is convoluted with the intensity of the underlying spectrum. Well, we think it's a Gaussian. You have some convolution function for your monochromator. And that makes doing these measurements quite hard. So that was a big takeaway that we weren't expecting from doing this. The transmission function is not symmetric in T, in wavelength. Okay, I'm going to leave this up for 10 seconds. And talk about the next interesting challenge we had. This was a showdown of great physicists, Fresnel versus Poynting, who has his all-powerful vector of truth, the Poynting vector. So we're doing this transmission, and we're averaging over S and P polarized light. P polarized light is what drives a lot of the interesting physics of polarized sunglasses. For some of the data, we have light coming in at an angle on silicon. Silicon has a high imaginary refractive index, whatever you want to call it. When we do the Fresnel equations, R plus T is less than 1. But there's no absorption. There's no classical attenuation anywhere in the system. So there's some missing light. But we are trying to really do precision efficiency in the UV. So we need to know if there's any missing light happening or where that missing light is going. And it turns out that in this specific case of P polarized light at high incidence angle on high K data, or transmission in lossy media using, well, that's different. This is a solution. Whatever, you're in that situation. There's a missing Fresnel fraction, and it's some kind of absorption in the skin layer. It comes from this near field, far field thing, and it doesn't include all of the intensity of the light. If you do the full solution for the Poynting vector to get the transmission through an interface, R plus T is conserved. Wow, Wakar's joining. Wakar, it's been so long. We went to school together. So you do this Poynting solution to convince yourself that the total amount of light is conserved. And then when we move back to the model, we don't want to do this 3D vector field solution because it would take 5 years to run the code. We actually can say the transmission is 1 minus the Fresnel reflectivity because the Fresnel reflectivity is valid over all phase space. This was a major, well, this just wasn't expected, but it was interesting. And, you know, Fresnel is not as all-powerful as we thought in this niche situation of high incidence P polarized light. So that's some interesting sidebars on the model. The model works, but also we have been using it and it's already proven quite useful, which is very exciting for me. I still need to do the final version of the paper, but it's impacting other papers, which is great to see. And coming soon is a teaser for my friend David's thesis, which is implementing the model to understand crosstalk in big DBCs. So we're at 20 minutes. That was pretty quick, but basically we can model the efficiency using all these inputs in math, and we can predict this complicated thing, the efficiency, quite well. Read my thesis for more info. Okay, SBC is this detector that I meant to show a photo of. Just kidding, I showed a photo of it right here. The SIPM sit outside those glass jars, and they're surrounded in CF4. Why do we have to do that? It's a long story, but the scintillating bubble chamber is a bubble chamber, obviously. And so it has to exist in a very finicky and specific thermodynamic range. So we need to control the state of the argon inside. We need a liquid that surrounds it to act as a pneumatic fluid, just like in hydraulic brakes. So it's a liquid CF4 that we use as a fluid, and it's a liquid. That's this, it's a liquid up here. These curves are the different thresholds that we operate SBC at. But liquid CF4 scintillates. So that could be a bad thing because it could pollute our signal, but it also could be a good thing because it could tell us about radioactivity that's happening around the chamber. Specifically, alphas, which are the bane of many dark matter experiments' existence, can capture on fluorine, which then gives you a neutron and sometimes a gamma. If this produces light, we say, hey, there was radiation outside the detector. Plug your ears for a little bit so we don't get tricked by these neutrons that are flying around. The nuclear physics actually looks like this. You have a capture cross-section of the alpha on the fluorine. You excite some internal energy state of the fluorine. Then it very promptly relaxes and gives you a gamma. And so you want to understand how much light is produced by either this alpha or this gamma. We have built a setup at Northwestern to study this. All credit goes to Zhihang Sheng. I helped with planning. This was during COVID. We kind of understand the expected emission mechanism of CF4 from what's happening in gas, and we know a lot about going from gas to liquid from the liquid noble side of things. So we make a couple of assumptions, and we can study the light yield. Very quickly, you analyze the data, you simulate the setup, which I've shown down here in Géant. You do some chi-squared scoring, and you can say, hey, the light yield is around 4 photons per keV for a gamma. So if a 10 keV gamma comes in, you'll make 40 photons. Some of those will hit your detector. Then you ask my previous model, how many of those that hit the detector are we going to measure? And then we can say, hey, at the end of the day, we can veto, close our ears to some fraction of the gamma and or alpha N events that are happening in the CF4. So liquid CF4 scintillates, that's cool. Beautiful, we have 25 minutes. Okay, now it's quiz o'clock. And you know what? We're gonna put Ryan on the spot because Ryan's so smart. Ryan, or maybe we could ask Gary, but Ryan's on Zoom with me. Okay, Ryan. These look like they're lined up, but they're not lined up. So this is like, the test on the assignment where you need to map the 3 things together: non-equilibrium static state, metastable state, and non-equilibrium steady state. Which would map to what?
Oh boy, non-static, metastable state, non-equilibrium, steady state. Oh man, you're putting me on the spot. I'm a recent grad student. I wish Gary was not on YouTube live stream so he could say this. Metastable state, would that be the SIPM?
That would be I guess it's not fair because you don't work on SBC. That would be the bubble, the superheated state. I should have put a label down here for superheated state. Okay. Because the superheated state kind of lives on its own. you don't have to put anything in to hold it like that. So the metastable is the superheated fluid. It's okay. You don't have to be on the spot anymore. The reason I put the voltage source down here for the SIPM is it's a non-equilibrium steady state because you're continually putting in energy. You have some input to keep it in a state, maybe like a secular equilibrium where you have something supplying the population. And then the trebuchet is a non-equilibrium static state. It's held. It's obviously not in equilibrium because when you pull the trigger, things are going to happen. So yeah, I'll spend the last 10, 15 minutes talking about something, well, near and dear to my father, and I guess me by proxy, which is releasing potential energy. And we'll take this as another example of model building. And if someone needs to build a model, they can look through these slides for general guidelines. The trebuchet, history's most polite way of saying respect my boundary conditions, turned gravity into projectile motion long before we wrote down the equations. That is not a quote by Einstein, but it's hilarious when things get attributed to him. So I'm going to show 2 videos of what this looks like, and then we will go into the model building. Here we go. Okay. So we built this. I'm not sure if the audio is included or not. So this was the first launch ever. We released the system. We have something very light on there and not a lot of weight in there. And it may have looked like a failure, but the fact that it moved and didn't break worked great. And we were able to throw this block and it went straight, which is good news. So the system works. We said, okay, it works. Time to beef it up. Let's see what we can do. And okay, here we go. Oh no, sorry, this is the same thing. That's me running out of the way because I don't want to get hit by the block. Here is the first real launch. And someone wrote, "Love you, Mom," on the side of the thing. Someone's thumb is in the way. So we rig it up, we load it up, we have a high potential energy, and we pull it, and we can really whip the hay bale pretty far. That's like a 30 to 50 pound hay bale. Let me move this out of the way. So the system swings down. It's like a double pendulum. You can see right here that the counterweight starts lagging behind. This causes a delay in the main beam. And the thing we're throwing, the hay bale on the sling, really whips forward. And if you could hear the audio, it goes whoosh, which is cool. Now we also have a lot of variables in this system, which I will list in a second. First, I need to list for anyone who wants to do this at home, the safety considerations. The rule of 2, which is beer, fire, music. You're only allowed 2 of 3. If you have all 3 going at once, something is going to go wrong. The loading algorithm is actually very complicated. So that's it. For honestly, most things in your life, you should never have all 3 of these going at once because it's going to be too crazy. So this is the first flaming hay bale we did, and now it's showing up as a, here we go. So if you could hear the audio, you would hear that there's no music because we have fire. And that's a pretty good throw, although we're still on version 1 of the setup. But you got some gasoline on the hay bale. We have some good airtime there. We're still not throwing over the burn pile, so we can do better. So we did a major improvement in 2023. We reduced the mass of the swing arm by replacing the upper, I believe, 16 feet with a thin bar of metal. We measured what the deflection angle would be when it's fully loaded. I had to learn some quick civil engineering. And my engineer friend, Connor Martin, told me after I did all the math, I'm at least 2 orders of magnitude from the yield strength. Because we don't want to be loading this thing down with 3,000 pounds of weight on the end and have the counterbeam fail. Our nominal load is 2 layers. So, I wish I could show all the details of how to load the thing, but we will have to be satisfied with this video that I will scroll through. So this really is, we have 3 ropes. We have some pulleys that we have to rejig every time we do it. So it's 1, 2, 3. Then the rope comes all the way out to a tractor, or if you have 6 dudes, you can load the thing. We load it up, we get ready to fire, we're good to go. There's also many interesting things we discovered. But one of the interesting things we discovered, which really is a great first-year physics problem, which I was never given. If you have a rope here and you are pulling at whatever angle, you're not moving on the ground when you're pulling down, the tension in this rope will always be the same. It doesn't matter what angle the main swing arm is at. It doesn't matter how loaded it is. If you're standing near and you're pulling on an angle at the start, or if you're standing away, the tension in the rope, how hard it is to pull down, will always be fixed. It's a bit of a brain teaser, so I'm going to leave it there. There's some kind of symmetry of the system, you could argue, why things cancel out. If someone's taking a first-year course, they should put this in there. The rope we purchased was underrated, but it didn't break. So that's awesome. The second interesting thing when it comes to building a trebuchet, I stopped my timer, which is fine. The second interesting thing is that the amount of potential energy available does not depend on how long your counterweight sling is. It just changes the dynamics, right? If this is swinging, it's only this, the counterweight can only drop this distance, this horizontal distance. Making the counterweight longer just changes the dynamics of the system. Really, you want your weight moving as vertically as possible for as long as possible. And that's why you might see videos of people building trebuchets on wheels, so the system can move and the center of mass of the system stays in a vertical plane. So we did some upgrades and we made this length a little bit longer to get a bit more whoosh happening. So these are all the variables that we can change on a day-to-day basis. How many rocks are in the heavy weight? What are we throwing? How long is the thing we're throwing? And what is our load position? So first I want to show what the simpler version looks like. Like I said in step 1 of model building, is you have to simplify the system. So if you just have a pendulum or a seesaw, which is this, and you plot your angular velocity, radians per second, this is the angular velocity of the main swing arm. You see, it's very mellow. It's like a pendulum. Pendulums don't have any crazy, sharp motion to them. You add a layer of complexity. You add the hanging counterweight, and you immediately see that this angular velocity gets much sharper, right? The beam goes whew, and it has a kind of kink at the top, which will become our launch point. Finally, you add the sling, which is down here on the lower left. And really the variable we end up caring about is psi dot, which is the angle of the sling, and that whipping around really is what gives you your velocity to throw these things quite far. And you can see this red line, which is very sharply peaked. It looks like a resonance. If you make the central swing arm very light, then the system can get moving quickly. And these sharp peaks, these like, almost resonances in psi dot, the angular velocity of your sling, is really what you care about. And when people are throwing things at Mach 2, they have incredibly sharp curves here. So I already solved the equations, but the Lagrangians look something like this. We won't go through it term for term because we don't have time. But Lagrangian mechanics definitely works, which is truly incredible. So we did some launches. I think I'll show another launch video. And we tried to do some data taking. But this was in 2022, 2023, probably when I was considering dropping out of school. And, data taking, this is not, we do this to avoid the scientific rigor of our life, of my day-to-day life. But we did take some data. Here is one video to whet your appetite. It's a beautiful day. Okay, here we go. And that one has pretty good loft on it. I believe that's a 150-meter throw. You can see it goes quite far. And we can again look at this and you see it legs out. The counterweight gets left behind. Let me see if I can zoom in on this. The release happens. Oh, come on, baby. The release happens, the counterweight gets left behind, and we get the whip forward. The projectile comes off somewhere around vertical on the main beam. Maybe a little bit before. Sometimes it comes off a little bit after, depending on how you tune the variables. So we want to solve these ODEs and see if we can get some of that behavior out. So we took all the measurements as far as I could remember of the trebuchet, and we put them into this code I built, which I built in one day. And on the top, we have the angles, so not the velocities. And as we drop the system, this blue line is the angle of the main beam. You can see it starts to straighten out. Then this upper curve is the counterweight. And so you get this little bump structure, and that's when the counterweight swings back. It's now having to move horizontally and it gets delayed. And then the main beam stalls out. As it stalls out, the sling gets whipped around. And if we look at the angular velocity, the derivative of this, you can see that the main swing arm in blue and the counterweight in orange are positive and then negative, which means they're rotating clockwise and then counterclockwise. The sling, it has this slight inflection point, which you can tune out depending on your input variables, but you get this nice sharp resonance. And that is where we define, I shouldn't call it a resonance, the molecular people will be angry. You get this nice sharp peak, and that's where we define the release. Defining the release point, is a little bit nuanced, but we'll say it happens at this peak. Experimentally, we did see that if the rope was too short, we could accidentally throw directly upwards. So this is an example of a shot that goes backwards. And we had made the sling too short. There was fire and beer, so no music. And you can see about here, the thing's coming down, the counterweight starts lagging behind. Because the sling is short, the mass has caught up and it's already moving up. It's not getting pulled forward. And the projectile gets thrown, it still goes forward, but at a very, very high angle. We have another video of what I'm calling a peak release. Nope, stay there. Okay, and as we go through, that has a lot more forward momentum. I think that's the video already showed, but I'm going to pause here. It's coming off, and the system is vertical or maybe slightly forward. And then here we have a forward release. And if you ask me what the experimental conditions were for these throws, I would not be able to tell you. But this was a good one. The system drops. The counterweight swings out. The system lags. And now you can see the granular projectile is way lagging behind. It stays on for longer and it really gets whipped forward. And it comes off here when we're maybe at about 5 degrees forward. Because of air resistance, that's the throw you really want. So let's see if we can get this behavior out of the model. This is just showing what I just showed. You get some of this qualitative behavior we want to see. This figure is too small. Let me go bigger. But this is a plot of the angle of the main beam at release as we vary the sling length. And you can see when the sling is short, we're throwing when we're backwards. These values are positive. And as the sling gets longer, we start throwing forward, which is what we saw in the data. This is great. However, your speed also varies. This is the peak of that resonance of the sling whip. And you can see it starts to fall off. So yeah, you can throw more forward, but as the sling gets long, you have a huge lever arm and you can't generate as much velocity. So, you have to balance out these two things. But this is good. The qualitative behavior we saw exists in the system. We can define the release point. That's all good. So I did measure 9 launches and I found them in my old book. If any undergrads are watching, when people tell you to keep your old, lab books and you're like, whatever, that's crazy. I found my notes wherever they are from many years ago, but the sling lengths were written in here, which is incredible. I also wrote them on these little flags that we put in the field. So it's hard to see in this photo, whoops, but there's a bunch of flags in the field denoting the marks. I had already built a integrator to do air resistance projectile motion. And so I said, okay, I'm going to put these variables into my equation for this system. I literally asked ChatGPT, I said, hey, what drag coefficient should I use for a rock about 8 inches by 8 inches with a long sling attached to it, a 5-meter sling? It said, use 1.3. I said, sure, I'll try 1.3. I input this in to the code. I plot predicted distance as these dots versus measured distance. This line is perfect prediction. And as you can see, the prediction of this code that I wrote in a day is between the data points. In physics, we would do a bunch of statistics and say, hey, is this within significance? I'm going to say, yes, it is within significance if you normalize for the work input. And this really blew my mind because it's still so amazing that physics works sometimes. And I'm not including friction of the beam. I'm sure our estimated center of masses and beam moment of inertia are not exact. We have the exact angle we're loading it at, but it still works, which is insane. These are all about 150-meter throws, 130 to 155-meter throws. And one day I was feeling crazy and I said, hey, Dad, we got to go we gotta go for a big throw. Like if we snap the system, who cares? We gotta load it up with 60 retaining wall stones. This is not quite a world record throw, but it's pretty good. This will let you see about how big the rock is. It's a big, like retaining, yeah, whatever, it's a big brick. We put a bunch of divots in the field that we had to fill after. So I said, Dad, we got to fill this thing up with thousands of pounds of weight and see how far we can throw it. And if you light it on fire, it decreases wind resistance. And so that was a 170-meter throw, and the system didn't break. You can see there's a lot of potential or kinetic energy remaining in the system. You kind of get these out of phase modes, which are kind of cool. But it was it's the world record for Ottawa. Of course, I have no idea what the sling length was when we did that throw. So let's call it a nuisance parameter. We're physicists. So I estimate the projectile distance using my code for a variety of sling lengths, and they cross the line. So physics really works. It's amazing. It's incredible that people also got these working so well without just by trial and error back in the day. I've been talking forever. I'm sorry about that. In summary, in the simulation era, I think there's still room for analyticity. Way back, we built this photo detection efficiency model. It works. It's used in experiments. It's providing results. And, as a model building walk in the park, you can do this for projectiles as well. And computers truly are incredible. And I love model building, and I love when stuff works. And I think that's the beauty of physics. There's a lot of other trebuchet analysis we could do, like scanning parameter spaces, and there's all these different modes. What happens when you have an inflection point here? How sharp can you make this? But that's at least 2 days of work. So that's it. Thank you, Ryan. I know I'm over time, but I think it was worth it.
Honestly, I think it was worth it too. It was really cool hearing about the trebuchet. For anyone in the YouTube live stream, if you have any questions, I'm monitoring the chat. So if you'd like to ask Austin any questions about any portion of his presentation, feel free to type that out. If anyone in the Zoom call has any questions, feel free to put your hand up. While waiting, I have like a quick, I guess, initial question is, so how do you know of what the Ottawa record is for trebuchet? Is this a regular thing happening over in Ottawa?
No, I've started saying, it's a national capital region record for people with the last name de St. Croix, at least.
Perfect. Good to know. Good to know. While waiting for potentially some other questions, I also had a couple more actual physics-based questions.
Yep.
So when you're doing your measurements for your photon detection efficiency, part of that is you have to know how much light your SIPMs are being
hit with
or are being exposed to. So how do you measure the total exposure the SIPMs should be having at that moment?
Or you mean the light flux? How do we measure the total light flux?
Yes.
Yeah. So this here is the VU-V4 that we're measuring. Right here, we have a diode that's calibrated by NIST. So it's a photodiode. It's 1-to-1 on the current. Well, not 1-to-1, but it's not a avalanche detector. So we shine the light on the diode first to see what the light intensity is. Then we move on to the SIPM. And we go back and forth because the lamp intensity slowly changes over time. That's why the data is limited to 350 to 830 nanometers. We would obviously love to go down to 120 nanometers, but the diode was not calibrated down to that scale yet.
Got it. Perfect. Thank you. Are there any other questions? Anyone in the Zoom call have any questions? Looking at the chat. Nothing. Oh, Adam's got a question. Perfect. Adam, go for it.
Hey, Austin. Nice to see you. I missed the first half, unfortunately. I got the times wrong. But during
Yeah,
your
don't worry about it.
trebuchet extravaganza there, you mentioned that the fire reduced the coefficient of drag. Was that true, or was that just a joke?
That was just a joke, but I have thought about it quite a bit. And yeah, I thought about it, and I wish I could think about why it's the case or not. I don't know if you know about any fluid dynamics.
No, I don't. I caught that and I wondered if it was true.
No, it was a joke I just thought of. Yeah.
And another thing, do you have any guesses as to why you were mentioning that the angle at which you pull the tension in the rope is the same?
Oh, I know why
guess
it's the case. Yeah, I mean, yeah, we could explain
okay,
it.
but it's an open question.
No, it's more like a nice brain teaser. You know, it's not too hard to think about when you're on your going for a run or whatever. You're in the gym. But actually, now that I think about the fire thing, the reproducibility of the trebuchet is extremely good. Like, we'll do 2 throws at 144 meters, one after the other. Like, literally, the rocks land a meter away from each other, and we have done it with it on fire and not, and they do go within 1% of each other's distance. So I actually think the fire doesn't change it. What did I say? I should have added more drawings here, but you know, you can imagine when the beam is straight up, you're pulling at an angle, and it's easy to pull the beam because there's not a lot of torque against the counterweight, but you also are pulling with very bad torque because you're pulling straight down on this beam. As the beam gets down, the angle you're pulling at becomes more favorable, but also the angle of the counterweight becomes more unfavorable, and the two terms cancel out. So, you know, if you're pulling straight down on a beam that's up, or you're pulling straight down on a beam that's sideways, or you're pulling straight down on a beam that's upside down, the angular dependence cancels out.
Very cool. Thank you.
All right. If there are no other questions, I think we will leave at that as 4:29. Thank you again, Austin, for the great presentation, and thanks for everyone who joined us, whether on Zoom or on YouTube. We will be saving this recording on YouTube if you ever want to visit later and think a little bit more about Austin's trebuchets, equations, and free body diagrams. Thank you all, and have a good rest of your Thursday.
Thank you, Ryan. Thanks, everyone.